शुभं करोति कल्याणम् आरोग्यं धनसम्पदा शत्रुबुद्धिविनाशाय दीपज्योति नमोस्तुते.
On behalf of Center of Resource Development for Educators, I, Mrs. Uma Mahesh, welcome you all to our 21st session of Tuesday webinars. Before we begin with our session, a brief about Center of Resource Development for Educators. CRDE is the initiative of educators Dr. Suresh Nair and Mrs. Deepa Desai. Highlight a few points on Dr. Suresh Nair, the president of CRDE. Dr. Suresh Nair, a state teacher awardee, joined Vivek Vidyalaya and Junior College in 2006 after serving for KC College for about 18 years as a professor of physics. Dr. Suresh Nair is an able administrator and a perfect educationist whose visionary endeavor in the field of education paved the way to fetch him an array of accolades. He has guided thousands of students in the subject and is instrumental in popularization of science among the school and college-going students by conducting various Olympiads. He is a co-author in physics textbooks for junior colleges and MHTCET for engineering student entrance examination. A dynamic professional with more than 32 years of experience in educational services and enriching support systems for effective school and colleges operations. He has abilities in harmoniously managing tasks of profound best practices to effectively run school. A brief introduction about the Secretary of CRDE, Mrs. Deepa Desai. Knowledgeable, insightful, hardworking, determined are just some of the words that describe Mrs. Deepa Desai. She has been in the field of education for the last 37 years and is a recipient of many awards for her work. Former principal of Arya Vidya Mandir, Juhu, the founder principal of Mahapragya Public School, Kalba Devi, a CBSE school in South Mumbai, and former head of IES Manik Vidya Mandir. She is a woman of many talents, an inspiration educationist, passionate teacher, motivating leader, and a compassionate person. She is of the belief that every child can learn and has the potential, but must be taught the way they understand. Her rich experience as an educationist also made her innovative and knowledgeable trainer for the CBSE and Sri Kelwani Mandal's group of schools in Sherpur, Dhule. Center of Resource Development for Educators is a platform where teachers and educators are manured to excel and mentor the student community through local and international mentorship. CRDE offers opportunity to experiment and implement ideas, innovation and collaboration to achieve performance and continuous professional excellence. It is where confluence of like-minded individuals share and imbibe knowledge, experience through interaction, deliberation, and international exposure. A very eminent speaker for today, Dr. Rita Malhotra. Let me introduce Dr. Rita Malhotra, a mathematician, a poet, essayist, and French-English translator, is a former principal and professor of mathematics, Kamla Nehru College, Delhi University, postdoctoral fellow, University of Paris, and visiting fellow Mathematics Center for Advanced Studies, Punjab University, Chandigarh, and visiting postgraduate faculty, Delhi University. A PhD from Delhi University She is a recipient of the National Science Talent Scholarship and the National Scholarship awarded by the Ministry of Education, Government of India. Dr. Rita Malhotra is currently academic advisor at 𝐓𝐫𝐞𝐚𝐬𝐮 College, Chennai, executive committee member, the Poetry Society, President Poetry Across Cultures India, and World Poetry Ambassador to India. She has 14 published books, including 2 books on mathematics. Her literary writings, globally anthologized, have been translated into 13 languages, including Japanese, Hebrew, Serbian, Hungarian, Romanian, French, Spanish, Bengali, Oriya, and Hindi, besides others. She was included in the 2020 Kali project by Candace Louisa and Team Pennsylvania, and more recently, her poetry has found a place of repute in the Digital Humanities Initiative called Life in Quarantine, Witnessing Global Pandemic of Stanford University, USA. Her piece, Poetry, was included at the Westminster Arts Council and was later on the display at the John Lennon Peace Tower, Iceland. Dr. Rita Malhotra's poetry constitutes a section of a Mumbai University English Literature doctoral thesis on ecofeminism and finds mention in several literary research papers. She has been invited delegate at writers' conferences across continents. She has been honored by the World Congress of Poets 2019, the Distinguished Visionary Poet Award by Writers International Network Canada 2013, the honor by the Ministry of External Affairs, Government of Romania 2012, the Women Achievers Award 2020, besides others. Malhotra has translated and co-translated poets across the world. Recently, on 23rd March 2023, she was invited to chair a paper presentation session at the international conference organized by the Foundation of SAARC Writers and Literature in New Delhi. Her latest talks include the Platinum Jubilee Lecture on Poetry, A Path to Women's Empowerment for GM University, Odisha. Latest developments in the field of natural sciences for the Russian Center, Delhi, on the Indian culture for SHOAM at the British High Commissioner's Residence, Delhi. Malhotra's talks are broadcast from time to time on the GOS services, the English Talk program, and the national channel of All India Radio. She has been interviewed on the television in Belgrade and China. Dr. Rita Malhotra has traveled widely across the world. She speaks Bengali, Hindi, Punjabi, English, and French. We are indeed privileged to have you, ma'am, today to speak on the topic, Infinity, a treasury of intrigue and interest. I'm sure we all will have a wonderful takeaway from you today. Over to you, Rita Malhotra, ma'am.
Thank you so much, Umesh, ma'am. Is it Uma Mahesh, ma'am? Thank you so much. Lovely words, but yes, I'm a mix of, poetry, maths, and a little bit of French, which I teach in Mumbai, by the way. Yeah, let me begin right away without taking, but thank you, CRDE, and thank you, Deepa, ma'am, and then now Uma Mahesh, ma'am.
You're most welcome.
Privilege among such distinguished people. So I straight away start. I'll try not to be too mathematical, but in case there are some people from the mathematics discipline in the audience, so once in a while I will say where I'm, kind of addressing them directly. But so let me begin with infinity. Yes, first of all, we still haven't understood infinity very well, but a lot of attempt has been made and research is still on. So we begin with numbers. We always say that numbers are the highest degree of knowledge. Sometimes we say that numbers are knowledge itself. Today, why I'm talking of numbers, because ultimately it's the numbers that are going to lead us to infinity. But mathematics is certainly not only about numbers. It's an endless, open-ended journey. And with a lot of the edifice, of course, is here to stay. And so I'll straight away go to the ancient times. And this is the about the Hottentot tribe, according to certain African explorers. There's a story that goes that, there were two people of the tribe working in the fields, perhaps. And one of them asked the other person as to how many children do you have? So the person took his time, thought, counted one, and then he stopped at two and he said, I have 2 children. When the first person was asked the same question, he kept pondering, kept wondering, and he could not give a number as an answer. So he just said many. That is because he had 3 children. So you see, there was, no counting beyond 2 or 3 in those days. But of course, that's the ancient period, and it is very amusing for us today. Again, coming to the ancient accountants, they were always confined to a few thousands in their calculations. So even if, somebody was trained very well in arithmetic, I'm not talking mathematics, they would still be very embarrassed if they were asked to write a figure like 1 million on 1 crore, because as I said, they never had to encounter such numbers. But why all this appears so amazing, or not amazing, but amusing to us, is because we are so used to big numbers. But before I go to the big numbers, one more story here, and that finds places in many of our books. This is about King Shirram of India, as you see in the title of the slide. So he was very fond of the game of chess, and he was very impressed with the clever moves, so many clever moves that were possible in the game of chess. And he realized that his Wazir, Sisa Ben Dahir, was the founder of chess. In fact, chess originated somewhere in 600 BC during the Gupta dynasty. But that time, it was called the Chaturanga. That was the precursor of chess. So anyway, he called his Wazir, very impressed with him, and he wanted to reward him. So he said, okay, you can ask for anything. Now, the Wazir was a very, very intelligent Wazir. So what he said is, okay, give me 1 grain of wheat to keep on the first square of the chessboard. Give me 2 for the second, 4 for the third, 8 for the fourth, and so on, So basically, he was saying 1 for the first, which is 2 to the power 0, 2, that is 2 to the power 1, and then for the third square, he asked for 2, 2 to the power 2, and so on. The king was very happy. He said, okay, at least my wealth is not going to be affected, kind of a reward that he has asked for. Now the counting began. And believe me, by the time they reached the 20th square, they almost realized that all the crop of India would not be enough to fulfill the desires of the Wazir. So it was days, but as I said, that now we are used to such big numbers, and Googology, as you see at the title of the slide, it is actually the study of the nomenclature and properties of large numbers. And we are accustomed to large numbers like the total number of atoms, which stands between 10 to the power 78 and 10 to the power 82. In fact, Google is actually 10 to the power 100. And you'll be surprised to know how this term was coined. What happened? This was an American mathematician, 𝐓𝐫𝐞𝐚𝐬𝐿. So he just asked his 9-year-old nephew, just try to give me a name for a very, very big number. And a 9-year-old, what would he say? So he just came up with this word Google. And actually the mathematician Kastner, he mentioned it later in his works called Mathematics and the Imagination. And it is so surprising to know that today we are so used to Google. You know how this Google came? We spell it out as G-O-O-G-L-E. The founders of Google, you would all know, it's Larry Page and Sergey Brin. Both are, of course, business magnates, and they were from Stanford University. They had met then, geniuses, both of them. it was by chance when they were dealing with large numbers or talking about that, it was misspelled, mistyped as GOOGLE, and they decided to stick to it. So the original big number is spelled as GOOGOL, Google. Okay, so that's how we have our Google today. Going back to our India, we are always proud and we say that, you know, it was here that mathematics came in, the discovery of zero. It was Brahmagupta who was the first Indian mathematician and the author of the first text which actually treated zero as a number. Because you won't believe, nobody was ready to take zero as a number. They would talk of it as nothing, or it represents nothingness. Somebody would say, I mean, how can nothing be something? So we are not going to include it in any text. Forget calling it a number. But that's why when Brahmagupta, you know, actually mentioned it as a number, it created a huge commotion in the mathematical fraternity. Some would not accept it. There were hostilities and all. But today, surprisingly, you'll be surprised to know that there is a foundation which is based in the Netherlands. It is called, I've written the name here, ZeroRich India, where they are studying the origins of zero. So that is so fascinating. But why I mention zero is because we always say that it is not possible to ponder infinity unless we have pondered zero. One, of course, advantage of zero is that it helps us create big numbers. As we just now saw, 10 to the power 100 is a Google. But there is another advantage of zero, and that is it forms the cornerstone of calculus. So anybody familiar with calculus or the simple differential calculus, which is studied in schools also, you know, will know how important zero is, because all the time we're talking of the concept of limits as a certain distance tends to zero. And therefore it is so, zero is almost a celebrity for us. Number 3, zero is the basis of computer programming. Where would computer programming be without zero? Because it's totally based on the binary system, which comprises 0 and 1. So we'll first talk about some conceptions about zero, especially where the philosophers were concerned. Sorry, not zero, but infinity. So why did I speak about zero? Because zero is going to take us to the big numbers, and through the big numbers, we are going to approach infinity. Now, what did the philosophers think? So I cannot take up all of them, but some significant ones. Let us take Pythagoras, for example. We are all familiar with the simple Pythagoras theorem, which is taught, I think, in 7th or 8th classes. He considered 1 as the generator of all numbers. So he says you go on adding to any large number, you add 1, it will give us another large number. And therefore we can create numbers, larger than the previous one, and so on, continue. But he did not use the word infinity or something that we are approaching to. He only confined himself to the large numbers. Then comes Aristotle. Now, Aristotle, of course, Plato had also taught him. He believed in Plato, and many of the philosophers always associated God with infinity. And for them, because God was the absolute infinity and there is only one God, so it is one infinity. That was, usually their interpretation. Now, when Aristotle came, he totally dismissed the idea of anything called absolute infinity. He said, if at all there is something, it is only potential infinity. What did he mean by potential infinity? He just said that you keep counting upwards, you're going up and up and up, and therefore you're creating larger numbers. But since the world is finite, time is going to run out, and infinite God has not been able to create any infinite object, so there is nothing called infinity, and it was totally dismissed. Then we come to this German philosopher, Nicholas of 𝐓𝐽𝐬. We mathematicians are very fond of him, because even as early as then, we were talking of the 15th century, he said that yes, infinity is something that is limitless. Since it is limitless, it has no limit. So the world is part of that, infinity. And he also, because he was influenced by Aristotle, Aristotle was influenced by Plato. So he said, yes, God, which is infinity, is actually a circle. So he said God is a circle with its center. Center of the circle is everywhere. Now imagine if the center of a circle is everywhere, where will the circumference be? So he said the circumference is nowhere. And as far as we humans are concerned, we are somewhere between the finite and the eternal. That's as much that as he could say. Even because of that, where he's brought in a little mathematics, he was a bishop of Cologne actually, and he was dismissed. He had to leave his job because of his interpretations, which differed slightly from the earlier philosophers. Now coming to our today. Today, what we all know, the counting numbers 1, 2, 3, 4 and all, and we call them the natural numbers. Okay. Now, if we know that it goes on and we cannot have a largest natural number, it doesn't stop. One more term I'm going to use here, that is the cardinality of a set. Cardinality is nothing but the size of a set. So if you have a family of, say, 5 members, we will say the cardinality of that family considered as a set is 5. If there is a 7-element set, we will say the cardinality of the set is 7. But then the question came, what is the cardinality of natural numbers? Till today, some children especially will answer, it is infinity. But that is a wrong answer, because infinity doesn't exist for us. So we cannot say that the cardinality is infinity. The second situation where infinity is given as the answer is when we ask, where do 2 parallel lines meet? Now, people will say they don't meet at all, or they'll say they meet at infinity. Both answers are wrong. What is the cardinality of a line? Line means most of us referring to the real line, which we teach again in the 7th, 8th standard, where we put a 0 in between the positive numbers on the right, the negative on the left. Now that also, we cannot answer the question if we are asked what is the cardinality of a line, because the line consists of all its points, and the points are all the real numbers that we are aware of. So how do we answer the card? So these answers will be provided today. And coming back to parallel lines, that's why I showed the railway tracks. Everybody, that if two friends walk along 2 parallel lines, will they ever meet? The answer most of the time will be no. That is a wrong answer again. Why? That is what we tell the children maybe, because all the time we are working on the plane of the blackboard or the plane of the paper. But if we walk on the Earth's surface, the Earth's surface is not plane. It is a curved surface. And therefore, sometime or the other, if they keep walking, if you think of it theoretically, they are going to meet. In fact, because of this curvature of the Earth's surface, even the Pythagoras theorem, the simple theorem where we say in a right angle triangle C square, the hypotenuse square is the sum of A square plus B square. We all teach our children that, at a very elementary level. Even that doesn't hold if we think of the surface of the Earth, because it is not plane. But yes, we teach them in schools because we are all the time working on the plane of the notebook or the blackboard. On a plane surface, yes, it is true. So all these questions somehow become unanswered, or they are not answered properly. So today we are going to answer them. Now, as a poet, I think we poets are always incorrigible. I'm sure among some of you also, there'll be people who are writing poetry, but I had to bring in William Blake here. You know what he says? To see a world in a grain of sand and heaven in a wild flower, hold infinity in the palm of your hand and eternity in an hour. Nothing is possible. So he says, if you actually want to see the whole world within a grain of sand, you should be able to hold infinity in the palm of your hand, or the eternity in an hour. It's both impossible. But I love the analogy that he has given here, and that's why I mentioned him. But we are going to pass on now. I'm just giving you here an example of the infinity mirror. You know why it's called an infinity mirror? It is nothing. It just gives an illusory effect. And in the diagram, especially the lower part of the picture, we can see these beautiful candles because we've taken the candle as the object of the light source here. Infinity mirror is nothing, but if we put it as if those images are receding to somewhere which we don't know, receding to infinity maybe. And here, why this is so fascinating and so intriguing, actually, when I say that the mirror images are receding in size, if you could look at the picture above the candle picture, the first image, the rectangles are showing the images, is bigger. Then if you look just behind it, you know, the images are getting smaller and smaller. So what happens is actually the width of each image. The width of each image is actually inversely proportional to its distance, where the image is being formed, to its distance d. So if the distance of the image is d, then the width of that image is inversely proportional, so it's 1 by d. And it has been proved that if you take the total area of all the images, the answer is finite. But if you just add up the widths of all the images, the answer is infinite. So imagine we are talking of something where, you know, the area is finite of all area taken together and the width is infinite. How does that happen? Again, the concept of infinity comes here, because when we are calculating the area, the concept of limit comes in. Limit as something tends to infinity. So I just thought I'll bring in this example because so many people, you know, use this candle, the concept of this infinity mirror and this illusion mirror effect. They even decorate their drawing rooms with this piece, you know. So now going back, if you see the first picture, you know, the images, the first one is broad and then it becomes smaller and smaller and smaller. So if we actually, with the help of geometrical optics, the series of repeating images that we saw in the previous picture, they form a kind of mathematical surface which is like a horn in shape. It is called the Torricelli's trumpet. And the Torricelli's trumpet, why? Because Torricelli was an Italian physicist and mathematician who had first studied this, and it was shown that the surface area of this trumpet is infinite, but the volume that it encloses is finite. So again, you know, something that really puts us in a jiffy, because we wonder how can it be enclosing a finite volume when its surface area is infinite. On the right, this is just for the people who are into mathematics and they have studied integration or they might be teaching integration. We have formulae in terms of integration for the surface area and volume. And this is how the volume and the surface area was calculated in case of the Torricelli's trumpet. And in the second calculation, if you see, we have written pi into 1 minus 1 by b. But b tends to infinity, and therefore 1 by b is kind of negligible. It becomes a 0, and therefore we are left with a pi, which is finite, so the volume is finite. Whereas when we see the area, surface area formula, and we actually calculate it, it tends to infinity. So these have been some of, you know, the aspects where it has intrigued us, and especially for a layman who's not into mathematics, it becomes unbelievable. But still we say infinity is beautiful. So I'll take you to something called fractals. What are fractals? You know, we see them everywhere. Fractals are actually complex patterns, you know, but they remain self-similar across different scales. And I will mention especially one fractal here, which is called the Koch Snowflake, because it looks like a snowflake. Some people pronounce it as Koch or Koch. The British pronounce it as Koch, because Koch was a Swedish mathematician, and he actually published his result about the Koch's curve, as it is called, in the year 1904. And we will soon see that 3 Koch's curve actually make the Koch's snowflake. I won't talk about its area and perimeter just now, but let us look at the first figure. You see, the first one is a simple triangle, 3 sides. It's an equilateral triangle, all sides are equal. Now, if you, from the first figure, we want to go to the second one, which is a star, looks like a star, what do? We take the side, we divide every side of the triangle into 3 parts. We delete the middle third, and on that middle third, we again construct an equilateral triangle. That's why you will see on each side of the triangle, you get an extra triangle, which is constructed with the help of the middle portion of the line. Again, that gives us stage 1. Again, with that star, each small triangle, if you think of, and their sides are again divided into 3 parts, and the middle part is erased, but there's a triangle constructed on the middle part. Then you will come to stage 2, which is the next figure, and the next again is stage 3. But I'll show you actually how it gets formed. This is how the Koch Snowflake is formed. So it begins with a simple equilateral triangle, and it's only a matter of division of the sides into 3 parts, taking the middle part. Actually, we are erasing the middle part, but constructing an equilateral triangle on that, and this process continues. So can you imagine that ultimately what's going to happen? The perimeter of the triangle, that is the boundary, that will be infinite because we are going on and on. But as this fractal evolves, we call it a fractal, as we said, that they are complex patterns. Across different scales, they remain self-similar, but we all realize that as we go on and on, continuing with the division process, ultimately, it will appear as a very smooth structure. But surprisingly, when we calculate the area of the fractal, it turns out to be 8 by 5 times the area of the original triangle, which is finite, because the original triangle has a finite area. But because we are continuing this process, endlessly, therefore, when you talk of the boundary, the perimeter, that will be infinite. So again, something very, very puzzling for us. But the concept of fractals is used. I've listed some of them in the growth of bacteria, in our brain waves, studying our brain waves. There are patterns in freezing water. There is a branch of, you can call it mathematics. It is called chaos theory. Most of the chaotic processes turn out to be fractals. And I've shown 2 pictures here. These are the fractals in nature. When we see such, here we are at finite levels, we can't go indefinitely. But if this design, is repeated, otherwise we don't get to see infinity. So that was, something that I've quoted here. And in our everyday life, our mobiles, because fractal antennas, if we have for our televisions or whatever, they receive all kinds of frequencies. And the concept is used in our mobile phones, in, of course, spacecrafts, the radars. In architecture, we have seen fractals in these structures. And Mumbai Airport always comes to mind. So this is how one aspect of infinity we are actually using, or we do see their presence in our daily lives. Now comes, you have to, if you're talking of infinity, we have to mention David Hilbert, German mathematician. Now, there are certain points that we have to keep in mind, and now a little bit of mathematics is coming in. Metaphorically, what do we say infinity is? We just say that it is something that cannot be attained, which even the philosopher said it is limitless. We can never reach infinity. But there is an axiom of infinity. That is where we begin, that at least one infinite set exists. And which is that set? We all know it is the natural numbers, the counting numbers, the set which we denote by capital N, which is 1, 2, 3, 4, and so on. So we know it exists. And the third point is nothing, it perplexes, infinity perplexes, because we have found the applications of infinity, the presence of infinity in so many areas and disciplines, which otherwise seem to be very distant from infinity. And here in this picture, I have put infinity vertically for lack of space. But yes, this is the symbol that is used, and we are all familiar with it. Now, a very, very interesting experiment that it has small variations in versions here and there, but why did he devise this experiment? Because he realized that, philosophers had radically different understanding. Mathematicians were treating them differently. There was, there wasn't much agreement. So just to adapt to the concept of infinity, he devised this experiment. It's very interesting. So let us think of an infinity hotel. Sometimes they call it the Hilbert Hotel because he devised it. Now, what does an infinity hotel mean? It means a hotel which has infinitely many rooms. Now, the night manager here is supposed to be very efficient, and he's always ready to please his boss. And night manager, extra guest, you can see. And so everybody says, no, there is no space. The hotel is full. But the night manager, he comes down, he says, no, I will be able to accommodate him. So what does he do? He shifts the guest in room number 1 to room number 2. The guest in room number 2 to 3 to 4. What happens in the process? Room number 1 gets empty. So the new guest is accommodated there. Now, one day, the hotel is full and 20 guests arrive, 20 new guests. Again, he says, yes, I will be able to accommodate them because the hotel is an infinity hotel. What he does, he shifts the guest from room number 1 to room number 21. So he adds 20 to the room number. Room number 2 goes to room number 22. 3 goes to 23. What happens in the process? The first 20 rooms become empty, and therefore the 20 guests can be accommodated. Okay, up till now it is fine. Now one day what happens? An infinite bus arrives with an infinite number of guests. So now what? For a moment he's puzzled, but then, he knows his mathematics. So he says no issues. What he does this time, he shifts guest in room number 1 to the number that is double of that. That means to room number 2. Number 2, he shifts to room number 4. Number 3 to room number 6. So what is happening now? Room number 1 got empty, 3 got empty, 5 got empty, because from each room the guests were shifted to the room which is the number double of that room. So all the odd number rooms 1, 3, 5, 7 get empty, and he just brings in the guests from the infinite bus, and one by one he puts them in these rooms, and his problem is solved. Now comes a more complicated case where one day there are infinitely many infinite buses that arrive and the hotel is full. Now what? This time even the hotel manager was puzzled, but he suddenly remembered that sometime in 300 BC, Euclid, and we all have studied Euclid's geometry. So Euclid, the mathematician, had said that the prime numbers are infinite in number. That's all he remembered. Now, what are the prime numbers? Again, we teach our little children the prime numbers, which they can't be divided, which have no divisors except one and themselves. For example, 2, 3, 5, 7, they are all prime numbers. They can't be divided by any number, except, as I said, themselves and 1. So he said there are infinitely many prime numbers. So let me use that concept to accommodate my guests. Now what he does, he goes to the hotel, he takes the first prime number, that is 2. The guest from room number 1 is shifted to room number 2 to the power 1, that is 2. The guest from room number 2 is shifted to 2 to the power 2, that is now room number 4. The guest from room number 3 is taken to 2 to the power 3, that is room number 8. That means, what is he doing? The powers of 2, those room numbers which are the powers of 2, they are being filled up. The rest become empty. Now he goes to the first bus. The bus, whoever is sitting in the bus has a seat number. They are infinitely many. Now he takes the next prime number, that is number 3. And now he brings in the first guest. First guest means guest on seat number 1. He gives him the room 3 to the power 1, that is 3. Guest from the seat number 2, he gives him the room 3 to the power 2, that is 9, room number 9. Guest number 3, who was sitting on room number 3, gets 3 to the power 3, that is 27, room number 20. And this is how he fills up all the rooms which have a number equal to the power of 3. Then he will go to the next bus, he will fill them up with the powers of 5. Then the next bus, he will fill them up with the powers of 7, and this continues. And therefore, what happens? Because we know in mathematics that the powers of no two primes overlap. So there will never be an overlapping of rooms, and each guest will have a room to himself. But there is a slight glitch here. Can you think of the number 6, room number 6? 6 is not a prime number, and 6 is not the power of any prime number also. So room number 6 will remain empty. So this kind of few rooms will remain empty, but he is happy. He says, my boss will be happy, the revenues will go up, and therefore the business will boom. So this is how Hilbert, first time, he devised this experiment. But can you imagine this happening if the hotel had only finite number of rooms, which in real life is true? This could never have been done, and extra guests would never have been accommodated. But this is the beauty of infinity, in fact. So now we go to, I just mentioned this was the hotel, and now we just, this is just to mention that there are many more manifestations of infinity in physics, in atomic physics, and very recently, can you imagine, there was a theorem which was enunciated in the 17th century. It was called Fermat's last theorem. Fermat was a French mathematician, and we all grew up on Fermat's maths theorem. Like for Pythagoras theorem, we say c square equal to a square plus b square. That is possible for a right angle triangle. So the next thing what occurred to us, are there 3 numbers a, b, c where c cube is equal to a cube plus b cube? That means c to the power 3 equal to a to the power 3 plus b to the power 3. Is this possible for higher, numbers higher than 2? Fermat had said no, but he didn't have a proof. And can you believe it? As late as 1995, Andrew Wiles actually has been able to prove Fermat's last theorem, that his thought or his conjecture, not exactly a conjecture, he had scribbled it in his notebook, it actually is true, and the proof has come. But in the process of the proof, he had to take the fact that infinite set exists. So he uses the existence of very large infinite sets in his proof. And that was a breakthrough, this thing. And of course, he's been awarded accordingly. And as I said, it occurs in, even now, you must be, often you must have heard that even physicists are wondering whether our universe is finite or is it constantly expanding? Is it, going towards infinity? All these research is going on, and therefore infinity has to make its presence felt everywhere. Okay. To the father of the arithmetic of infinity. He was the gentleman Cantor, again a German mathematician, and Hilbert supported him through and through. He was the one who actually gave, he brought infinity into a mathematical framework, a coherent mathematical framework. And there, the concept of cardinality was taken. As I mentioned, cardinality is nothing but the size of a set. So, of course, his theory is totally based on set theory. And 2 definitions he gave us. One was the countably infinite set. He said, what is countably infinite? If it is in a one-to-one correspondence with the counting numbers, the natural numbers. What do we mean by one-to-one correspondence? If I take a family, 2 families, each with 5 members, for the first family, first member, I can find a partner. In the second family, for the second member also, I can find a partner. We are not allowing anybody to have 2 partners from the second family. So this distinct member of the first family has a distinct partner in the second family. This is called a one-to-one correspondence. So he says any set which is in a one-to-one correspondence with the counting numbers, the natural numbers, is called a countably infinite set. We are not going to use this term very often after this, but this was his first definition. And he was the first mathematician who actually studied finite and infinite sets. He used and he showed us the significance of this one-to-one correspondence. Today we teach this in first year, sometimes in the 12th class or even in the 11th standard, the concept of a function, but that is beside the point. And then he gave another definition, but that we don't need, so I'm not mentioning it now. Basically, we want to know the concept of a one-to-one correspondence. We want to understand that because that is going to answer a lot of questions for us, okay? So now, this is just a slide telling us that mathematicians are actually now, they have built a bridge and they're still, you know, the bridge is going on, they're building a bridge which separates two kinds of mathematical statements. The finitistic statements, which deal with only finite numbers, what we see around us, the real numbers, and the infinitistic. So that is the bridge, and I found this nice picture, so I thought, why not use it? And then we come to equivalent sets. Now, supposing we are dealing, as I said, with two families, we are talking of the size of the families. We have two families with 5 members each, so we will call them equivalent. We can't call them equal because the members are not the same, but we can easily call them equivalent when we are dealing with finite sets. What happens in the case of infinite sets? Because we know they exist, we know our counting numbers exist, we know there are negative numbers, we know there are integers which are positive, 0, negative, and they are all infinite sets. So how do we define or even think of equivalent sets in the family of infinite sets? So let us see the first picture. If for the timing we can just forget the 0, this is the picture which was printed and I got it. Just let us think of the counting numbers. The first line, if you can see, we have written 1, 2, 3, 4, 5, 6. In the second row, we have written only the even numbers. And if we ask a layman, the even numbers are, they will say they are just a part of the natural numbers because we have taken only the even numbers, though the first set should be a bigger set. No. Here comes the advantage of a one-to-one correspondence. What is that correspondence? I said that in the first set, every member should be able to find a partner in the second set. One person cannot have 2 partners, or one number cannot have 2 partners. So once we are able to find distinct partners for distinct members of the first set, that will be a one-to-one correspondence. So we are showing in the figure, 1 can take its partner as 2, 2 can take its partner as 4, 3, 6, 4, 8, and so on. So in the second set, which is just the set of even numbers, which seem to be a small part of the total natural numbers, the counting numbers, has now become an equivalent set. So for us, in case of infinity, we don't distinguish between the natural numbers and the even numbers. They are treated as equivalent sets. Let us look at the third figure. I've taken a right-angled triangle here. Now, all the time, even when we are teaching our children, when they draw a right-angled triangle, we always tell them the hypotenuse, that is the slanting side, is always bigger than the other 2 sides, the perpendicular and the base. But for one moment, let us take a point on the slanting side, a point on the hypotenuse. You just drop a perpendicular vertical line from that point, we will get a point on the base. That means every point on the hypotenuse has a corresponding partner on the base, and therefore this, which itself is an infinite set, because between any 2 numbers we always have an infinitely many real numbers. So they are infinite sets, but they are equivalent. So for us, the hypotenuse is equivalent to the base. The hypotenuse is also equivalent to the perpendicular. We can just take a point on the hypotenuse and draw a horizontal line, and we will get a point on the perpendicular. The in-between figure, maybe it will become a little too mathematical, but just to tell you, after the integers use fractions, the rational numbers, we call them P by Q, etc. Even the set of all rational numbers, here we have shown only positive ones, they also can be put in a one-to-one correspondence with the natural numbers, and therefore for us in this picture, they are all equivalent sets. The naturals, the evens, the rationals, in the numbers, they're all equivalent sets. Now, one thing we have to come down from one-to-one correspondence to a very simple concept of listing. If we are able to list the members of any set, be they a family, of course, families are finite, but for any infinite set, if we are able to list the elements, list means put them in an order. The order should be such that we are sure that every number of that second set will occur somewhere. It will not be missed out. Then we are sure that we are able to list them. We will then say that that second set is a one-to-one correspondence with the counting numbers. Why? As you see in the first figure, the even numbers have been listed, 2, 4, 6, 8, 10, 12. Once we have the list, the counting number 1, natural number 1 will be taken as a partner of the first member of the list. Number 2 will be taken as a partner of the second member, and so on. So every member will have a partner from the second set. They will have a partner in the first, from the first, and they will be in a one-to-one correspondence. So here, I just took this slide so that we can understand the significance of being able to list a set. This listing is very important. And in so many competitive exams also, sometimes in analytical skills, they will just give you a few numbers and they will say, from this pattern, you try to tell us what will be the number in the 100th position or the 7th position. That means there is a pattern, we can list it out and we can write out a number, and then this second set can be put in a one-to-one correspondence with the naturals, and they will all be treated as equivalent sets. But then comes the question, what about the real numbers? In class 7 and 8, we are introducing the real line. We are telling the child, here is the point 0. To the right, we are dividing the line. We are labeling them as 1, 2, 3, 4. To the left, we are labeling -1, -. All of us have studied this at a very elementary stage in school. So Cantor asked, can we say that even the real numbers can be, in a one-to-one correspondence with the counting numbers? In that case, they will also be equivalent. And, but then let us look at this. This is very interesting. Supposing we say, okay, we are able to list the real numbers. It is just a conjecture. We are not sure. If we are able to list the real numbers, we have to begin somewhere in the list. We don't know where to begin. What is the smallest real number? We don't know. So for the time being, let us just assume, I have given 0.113085, supposing it is the first real number. The second real number we are showing as 0.233. Whatever the list is, we will now form a new number. And look at the new number, which is in blue in the second last line. What we do is, we look at the first number. If after the first decimal position, if there is a 1, then in our new number, we put a 2. And if it is anything other than 1, we put a 1. So we saw the first number, which is 0.11. In the first position, it had 1. So in our new number, in place of 1, we have put 2. So we are sure that our new number cannot be equal to the first number. Let's go to the second number, 333. Now let us look at the second decimal place of our new number. Again, let us look at the second decimal place of the second number. It is a 3. If it had been 1, we would have put a 2 in our new number. If it is anything other than 1, we will just put a 1. So in our new number, we have put 1 in the second decimal place. Similarly, if you go to the third number in the list, in the third decimal place we are going to look, there is a 4. Since it is not equal to 1, so we will just put, if it is not equal to 1, if it is 1, we will put a 2. If it is not equal to 1, we will put a 1. So the third number has the number 4 in the third decimal place. In our new number, we are going to put 1 because 4 is not equal to 1. Had it been 1, we would have put 2. Now, do we realize here that the new number that we are making is not equal to the first number, not equal to the second number, not equal to the third number? What does it tell us? That whatever way we try to list out the real numbers, we can always generate a new number which is not in this list. So what does it tell us? That we can never put the real numbers in a one-to-one correspondence with the natural numbers, and therefore the list of real numbers or the size of the real number set has to be bigger than the size of the natural numbers. That means infinity is not just one, which is the usual, understanding. There can be bigger infinities also. And therefore, this picture shows, that my infinity is bigger than yours. And just let me share with you, because you've been principals and, such educated people. Recently, I was a part of the team where we were interviewing faculty members, recruiting faculty members for mathematics. So at least out of the candidates came, I can't repeat the same question for everybody. So, and they were teaching real numbers and numbers in, their classes, TGT teachers. So when I asked them that what is infinity, or is there just one infinity? They all answered, yes, there is just one infinity. So here comes, the significance of concepts. And in any discipline, you would know that the deeper we go into concepts, our concepts become clear, and that is how we are able to give the right concept to the students. But believe me, even when students used to come till the second year level, this concept was not clear, and we had to bring in the example of the rational numbers, which we just now showed, the triangle, the hypotenuse, and then they realized, yes, infinity, there is a bigger infinity. So we already know 1 is less than 2, less than 3. Aleph naught was the, Aleph is the first letter of the Greek alphabet. So Aleph naught was taken to represent the cardinality of the size of the naturals. And now we have seen that C, which is now representing or symbolizing the size of the reals, it is bigger. So this is now the order. So we have less than 2 up to Aleph naught, and that is less than C. Now the question comes, is there anything bigger than C? Here, I will not go into details unless there's a question from somebody in the audience. Then I'll go into the concept of the power set. And just to mention that for any set, we have a power set, which is always bigger than the set. And if the set has n elements, power set will have 2 to the power n elements. So that means if the real number has C elements, if that is the cardinality of the real numbers, then 2 to the power C will be a bigger cardinality. 2 to the power 2 to the power C will be even bigger. So even the sizes of the sets or the sizes of the infinities are infinite in number. That is, such a beautiful result. And as Cantor said, that finite properties cannot be predicated in all cases of the infinite. In a finite set, can we ever say that a part is equal to the whole? No. We always have to say that, but in infinite sets, we just now saw the even numbers, which are a part of the natural numbers, but they are treated as equivalent sets because there is a one-to-one correspondence. So there is a lot when we come to the study of infinities. And I was just mentioning higher cardinalities than C. As I said, the power set has a higher cardinality. And when you construct the power set, then the next power set of that set will have an even bigger cardinality, and this goes on. Why I've shown this little diagram, you can see at the top I've written 1, 2, 3, 4. So this is a set with 4 elements. Now the set itself and the empty set means which has nothing, they are always treated as subsets of a set. What were the other subsets possible? If 1, 2, 3, 4 is a set, 1, 2, 3 could be part of it, 2, 3, 4 could be part of it. So we have listed out all the subsets, and if we count them, there will be 16. Because this has 4 elements, and the power set always has 2 to the power n, that is 2 to the power 4, that is 16 elements, and we can count and see. That's why I just listed out all the subsets of a set with 4 elements. This concept should be given to the children, not what I've written on the right, because that becomes a little too mathematical, but from the diagram. I'm unhappy with the diagram because even though I took it from a book, the proportion is not very nice. But we have to tell our children that sometimes, they feel that because the real line, which I've drawn here, you see, it extends, indefinitely in both directions. So children get the impression that because it extends, to some limitless point, that is why it is an infinite set. That is not the answer. Here, just if you take that small segment between -1 and 1, we can just fold that part of the line, we can fold it to make it a set semicircle, then we can see that from the center of the semicircle, if we take any point P on the semicircle, which is actually a point of the segment -1, 1, we can extend that line from the center to P and have a partner on the real line. That means every point between -1 and 1 will have a corresponding point on the real line and vice versa. So just now we spoke of one-to-one correspondence. That means even this small line segment, which for us seems small, -1 to 1, or let us take any line segment AB on the real line, it is still an infinite set. And in fact, it is equivalent to the set of all real numbers. That is so fascinating, and people, will not believe it unless we bring in this concept in the infinite sets and show them. So even a small line segment is actually equivalent to the whole real line. The real line, in fact, is equivalent to the whole plane, the plane on which we work, the plane of the blackboard on which we work. But those are, of course, bigger proofs. And now I come back to, I call these people the bad boys of mathematics. Why? When Cantor came out with the concept of infinity, the one-to-one correspondence, he showed with proofs that the real numbers are a bigger infinity. Infinity is not only one, it has more sizes. That is when these people, the first one is Kronecker. Now, Kronecker, who was actually a member of the Berlin Academy. Later, he became professor of mathematics. He was heading mathematics. You know what they called Cantor? They said he's a fraudster, he's a swindler, because he's going to corrupt the youth. And Kronecker, which there are some, the Kronecker delta we study in mathematics. He was a good mathematician. He was, but he saw to it that Cantor is not taken as a as a colleague in his institute, because he said he will only come and spoil the youth and give them all the wrong concepts. The second one, he's a French mathematician, Henri Poincaré. He was a physicist, theoretical physicist, mathematician, a philosopher of science. Same thing came from him. The third one, Hermann Weyl, German mathematician, again a philosopher, and he was an engineer also, if I remember correctly. Then Brouwer, the fourth one, he was a Dutch mathematician. And the fifth one, who was okay, he was a philosopher, but he had studied aeronautical engineering. So his approach to philosophy was through mathematical concepts. He, even after Cantor died, he said, and I've written it out here, that mathematics is ridden with pernicious idioms of set theory. He would not take it. And, the others, the spiritual leaders, the other philosophers, the religious leaders, they all, kind of dismissed Cantor, because for them, God was infinity. Infinity cannot be more than one. And, therefore, all these concepts are just rubbish. But ultimately, truth prevails. And actually, in 1904, the Royal Society, they awarded the silver medal to Cantor. And because that time, that was the highest honor that any mathematics person could be given. And Cantor was honored. But they say that, because of so much hostility that Cantor actually faced, he actually became very sick. Reasons could have been others. And he remained sick till he died. And Kronecker, the first bad boy, that is my terminology. So he saw to it till his death that Cantor is not appointed as a mathematics professor in his institute. So these were the reactions. And but of course, Cantor finally got his recognition. And now today, there is a problem which is still unsolved till today from Cantor's time. Cantor had already given a conjecture. We have just now seen the cardinality or the size of the natural numbers, the counting numbers, which is 𝐴0. We have seen the size of the real numbers, which is denoted by C. And we have seen bigger infinities because of the power set. What about the case? Is there any set which has a size between 𝐴0 and C? We still don't know. So much research has gone. There have been two proofs. One person proves that this is called the continuum hypothesis, the continuity in the size of the infinities. one person, one researcher has proved that this conjecture cannot be proved. Another one has proved that this conjecture of Cantor cannot be disproved. So it cannot be proved, it cannot be disproved, but nobody has till date been able to prove it. Lot of work is going on, and there is one mathematician who feels that Cantor was right, but unless we get a proof, we cannot for sure say whether there is any size between the counting numbers and the real numbers, the real line that we come to. Now, Deepa ma'am, or, could you please let me know, I can stop here, I can go on, because the next concept that comes is the reciprocal of infinity, which gets a little harder, and it is actually proceeding towards some subject called the non-standard analysis, but I can always stop here if there are interactions or any questions. As you say, I leave it to you.
Yeah, I think we'll leave it open for the teachers to ask questions.
Right.
Yes. Anyone? I don't know whether any of them are mathematics people, but science I know. Dr. Iyer is a science person, but I don't know whether mathematics.
Is he from physics, Dr. Iyer? Oh, you're Madam Iyer. You are muted, I think. Yeah. I can't hear you. You're muted, ma'am.
Ambuja ma'am, please unmute yourself.
Yeah. Am I audible?
Yes, ma'am.
Yeah. Amazing command over the discipline. It's unimaginable. It's very intriguing. Okay. To some extent, I did understand, but as very often it went beyond. I tried my best.
Sorry.
Some portions went just beyond comprehension.
Ma'am, I have to tell you here that I had a very good friend when I was in, actually we did a postdoctoral in Paris, and there were, people from different disciplines of science. So we had a gentleman from physics. And when I interacted with him, he told me very beautifully, again, as you said, certain things went beyond my head because, that level of physics, we don't know. He says that, when they study the structure of atoms, in the study of, the structure of atoms, there are electrons revolving, in orbits, we always talk of a nucleus and the orbits. So, and the electrons keep jumping from one orbit to the other. That much chemistry I remember we did in atomic chemistry. But in that, there the concept of infinity comes in, and they ultimately have to, stop somewhere, because physics is all about the real world, So they don't really go up to there, but they do show that if this process continues, it is actually leading us to infinity. So I was very happy that, even a physicist is actually studying all that, or, they do encounter these things.
No, it became a little too mathematical. Trying to comprehend became a little difficult. Let me be very honest about it.
It's all right.
To some extent, I had understood and went along with you in the initial slides. Later on, it became a little difficult.
Yeah, actually, when the mathematical, but the one-to-one correspondence comes in, that's why we always say listing, the size. So we use these terms for students, so that initially they understand and then they pick up the mathematical terms. But I was a little disappointed that, teachers who've actually done their BSc Mathematics, MSc, they came for interviews, but their answers were also not up to the mark. And that is a scare, That's why when we sometimes, see our children in schools, concepts not being, incorporated properly. So I think that's why it's very important for all of us to go beyond what we are going to teach or, what we have learned. So this study is just my passion, because my own area has been programming. It's applied mathematics, my research and all. But because I was very fond of abstract mathematics, that is where poetry comes in. So that's why, infinities, on my own, all the time I would study this.
It's the
So
highest level of intelligence. Abstraction is the highest level of intelligence.
yeah,
As
yes, ma'am.
long
Yes,
as things are
yes.
concrete, concepts are concrete, it's very easy to understand.
Absolutely.
And where
that's
there is a
when
logic.
Yes. So people often ask me, how come it's poetry? You know, mathematics is so exact. I said it's abstract mathematics that can be connected to poetry. You know, the creative aspect.
Yes,
Yes,
very
ma'am.
creative.
Yes, ma'am.
Dr. Saroj, I think.
Yes.
Dr. Saroj, would you like to
Yes.
share whatever you
Yes.
just
No, no, I
put
was
it on the chat?
and I just want to, may I speak something?
Yeah, please, please.
I was just in fact going to ask you that the structure of an atom and how closely it is related to that, and on all those energy levels and things like that. It was crossing through my mind because I'm a hardcore chemistry person. So the topic was very, very relevant to, and I was just thinking that how I can incorporate with my students
Yeah.
and make the lesson more interesting and something new. X factor I can include into the learning process. Very, very
Yes.
interesting.
Yes,
Very
ma'am.
interesting.
My
Thank you so very
chemistry
much.
doesn't go beyond second year. You know, after second year, we had to leave physics and chemistry. So,
And ma'am, I would request you if you can share this, presentation. At least we will be able to connect with something, and definitely will, make our own subject connectivity with that. But what you have, is very comprehensive. You have done beautifully.
okay.
You have explained
Thank you,
everything.
ma'am. Thank you so much.
Thank you so
Thank
much.
you. I think it's the passion. That's all. Yeah.
Yes, Saroj ma'am, once we little bit of editing here and there if we have to do, because we just started
Yes.
it, and we
Sure.
will share it. We will surely share.
Sure, ma'am. Thank you so much.
Yeah.
Okay.
Anybody else wishes to say something?
Yes, of course. I mean, it was something for me. I'm an arts graduate, okay, with economics and politics. For me,
Yes.
Rita ma'am, really I've learned something, and especially I would say about the hotel one you said, na?
Yes.
Hilbert's experiment was really, that was something, which is really, I mean, how he could do that. I mean, with infinity, how you put this example, that
Yes,
was really
and he was
wonderful.
a genius, ma'am.
Yeah,
And,
that's what.
ma'am, do we have
Yeah.
somebody from literature here, English literature?
No, I don't think.
Okay, because
Anybody?
yeah.
Yes, I think. What about Lata ma'am? Lata ma'am? English literature?
No, not myself, dear.
You are literature, no?
No, not English literature. English is just one subject. That's it.
Okay, I think we can just take it to any book. Why English literature, I said, because there's another example, and that is, again, I had it, but then I removed it. It is called the monkey's theorem. It's nothing to do with a monkey, but the experiment is that if you let a monkey, you give it a typewriter, and because it won't know what it is typing, so it's a random typing, and let it continue, let it not stop. So theoretically, if you imagine, why I said English literature, because the example I had read said that, take up any novel of Charles Dickens, and you never know, because there are permutations and combination in what order one is typing, and somewhere maybe the whole text of a Charles Dickens novel will actually be contained in what he types, because he's typing the letters of the alphabet. It may take eons of years. So, these are the things as examples they're given. Today, we cannot bring in a monkey, but today, so we have, modified it, and we said, if there is any device that can go on typing in a limitless manner, maybe we can recreate Tagore, I am, by the way, a Bengali, so Tagore is very close to my heart. So I always bring in the Tagore example, that maybe we can, actually we'll find all the works of Tagore in that material which is typed limitlessly. But of course, in the finite world, it is not possible. Only I'm happy about the physicists, because, they always initially dismissed infinity, but now with the kind of particle research, and I don't understand all that, but now they're having to incorporate infinity and infinity concepts, into their research. So now that is, though they are dealing mostly with the real world. So that is it.
what struck me at the moment is a practical example in biology.
Yeah.
Cancer, where there is, a lot of cells, growth of cells, tumor
Yes.
cells. So that also becomes, to some extent infinite. And then
Yes. Yes.
lastly, I think the person collapses.
Right, ma'am.
Reaches
The
his end.
person dies. So, time finishes there for the person. But actually, if the growth continues, that is going to
Yes,
take you
yes.
towards infinity. Yes, ma'am.
Yeah, I think every discipline will have this,
Yeah,
concept.
some
But somewhere
concept
we'll have to
coming
discover.
in and
This just
somewhere we
struck
have.
me.
Yes, yes, yes.
Good evening, ma'am. I'm not a science student nor a literature student, but still, the examples which you gave can be incorporated in our daily, life. And the voice, your voice is so sweet and so melodious
Thank you.
that made me, continuously to be, it made me, it kept me listening to you.
Oh, thank you.
It was really very nice, very nice. Thank you so much.
Thank you. Thank
Oh.
you. It's a pleasure because we are not able to share this everywhere, no? So it's only
No,
sometimes.
really, it was very nice, very
Yeah.
nice, ma'am. Thank you so much.
Yeah, thank you. Thank you. But currently, everybody accuses me of moving away from mathematics and going more and more into poetry. So I say, it is my age because, the kind of rigor that mathematics needs, slowly somewhere you slow down. And that is my next passion. So maybe I'm giving more time there. But if there are any poets amongst you, please remain in touch. We have an organization called Poetry Across Cultures. In fact, our next program is coming on the 22nd of this month. So it's basically international because we call it Poetry Across Cultures. And I have been working with the embassies while I was in Delhi. Now I've shifted to Mumbai, though currently I'm in Delhi. And, we used to connect the poetry of their country with ours, just telling them that, the emotions are the same, but it is only the expressions that are different because of our different cultural backgrounds, So we've been doing those programs since 2007. And now I have started a series on Tagore and the world. So we've done three programs with Bulgaria, Poland was our last program, Hungary, like taking Tagore's translations in those languages, bringing them to the fore. People, our poets are reading, Tagore. So we connect with somebody from that country if we are able to, and they provide us with some of the translations. But ultimately, everything is read in English. This time we are doing pure poetry on the 22nd, where people are joining us from some other countries. We'll have Indian poets, each one reading one poem, one composition of their own, and one from the repertoire of their favorite poet, from overseas poet. So we'll get a mix of both, So, and, I have to share this with you. Our Hungarian poet, Dr. Maria, what she has done is she sent one of her own poems, okay, fine. And the second poem where she had to choose from her favorite poets, she sent us a Hindi poet, 𝐓𝐫𝐞𝐚𝐬𝐮's poet. And I was so impressed, I said, and then I got to know that she is perfect in Hindi. She studied Hindi and she's even teaching Hindi in a Hungarian university.
Wow.
So, you get to meet such interesting people.
That's real. That's it.
Yeah, yeah. So anybody in poetry could get in touch.
Ma'am, is it an online?
It is online. I will definitely share the
So that I can
link
share the link
yes,
with,
yes,
with
yes,
the
yes.
CRD group.
Yes,
I can
yes, sure.
share.
It is coming, and that's why I'm traveling to Mumbai on the 20th, and 22nd is the program. So I'll be in Mumbai then. Yeah, okay.
Okay, ma'am. Okay. And
Thank
it was
you.
really, let me tell you, it was really a wonderful session, as Ambuja ma'am pointed out. Yeah, towards the latter part, then it really went.
I can understand.
Yeah.
But it was wonderful. And as Uma pointed out, the allotment of rooms by the manager was wonderful.
Yes,
Wonderful.
yes.
Yeah, that really talks about how a genius he was, he could
Absolutely, you can imagine but now I have to tell you about this, that infinity has another connotation. It is a romantic connotation, and there are many jewelry pieces where the shape infinity because it denotes eternal love. So, I think it's good to end on that note because, at least we move away from
It's a good one.
Yes,
Yeah.
that's really good. That's really good.
Yeah.
Okay.
Yes,
Yes.
ma'am.
So I just took some pieces where I found them, So that's
Good evening, Rita ma'am. Good evening, Rita ma'am. I'm Suresh Nair. I'm very sorry I could not join. I just now I reached to home. I could not join for the session.
Okay.
I will try to get the record.
Okay.
So,
Sure.
yes,
So what I'll do
you
is,
can see the
if I
recording.
share, I'll share up to the, yeah.
Yeah. And Rita ma'am, sir is a physics person.
Oh, I wish you
so
were
he would
there.
have really enjoyed this
Yes.
I could have
session.
joined. Definitely, I could have joined.
I was telling our colleagues that I interacted with a physics colleague, and we were together in Paris, and we had a lot of discussions. So he gave me some examples from physics, atomic physics, and we're talking about atomic structures or the changes or the electrons moving. There he brought in the concept of infinity. I have it written down somewhere. I'm going to go to Mumbai and look for that file of mine. So that was very interesting, but that is all that I could understand, and finally asked him to stop. So yeah. Okay.
But a wonderful session. Wonderful.
Thank you, ma'am.
Ma'am.
Yeah. Yes. Good evening. Good evening, Dr. Suresh Nair.
Good evening. Good evening. Good evening.
Yeah. Welcome. Yes. So, after a wonderful session by Dr. Rita Malhotra, we come to the closure. From the bottom of my heart, on behalf of CRDE, I thank Dr. Rita Malhotra for such a wonderful and depth about infinity. Really, for me, it was something very abstract, but you have brought some concrete concept on infinity. Thank you so much, ma'am. And also, being a poet and a mathematician, oh, wonderful combination. Thank you so much.
Thank you, ma'am. Thank you.
Let me thank Dr. Suresh Nair, Mrs. Deepa Desai for giving me an opportunity to host this webinar. Thank you, Lata ma'am. Thank you, Ambujam ma'am. Thank you, Saroj ma'am. Thank you, Shankar sir. And thank you, one and all. Last but not the least, thanks to the technical support. Always, they have been there for us. Thank you so much.
Thank you, ma'am, also.
Yes, you're most welcome. Yes. Thank you. Welcome.